Okay, good afternoon, everyone. So let's get it started. So before the lecture, I want to make an announcement. So the programming assignment number 1 is released. So you can see this assignment in Canvas, okay? And the due date is February 25th, midnight. So make sure you start early and, and submit this assignment on time, okay? Just a few quick things to go through. I don't know if you guys have already go through this assignment, but I can quickly go through the first assignment because some of you don't have any prior experience working in computer vision or deep learning. So for the first assignment, we'll do the chest X-ray image classification for the pneumonia detection. So we are using this chest X-ray data set from Kaggle. Okay, so you can download this data set from Kaggle. The link is here. And the data set is already being split. So you have training, validation, and testing. Okay, so you are using the training set to train your model, using the validation set to kind of, tune the parameters, right? And, we talk about like you can observe the validation loss or accuracy, see if your model is overfitting or or maybe even underfitting. Okay, so that's the validation set is used for. Okay. And because we are using classification, so you can apply any off-the-shelf CNN architecture. Because I think you guys have limited computing resource and most of you will just using Kaggle on those free GPU and Google Colab, right? So I suggest using smaller networks like ResNet 18 and MobileNet. We talked about MobileNet in the last lecture, right? Because of the computation efficiency. And also this smaller network may reduce the training time, right? So if you have a large data set, you have a large network, it may take longer to train. So because you also have to like tune the hyperparameters, right? You need to run the network maybe a couple of runs. So, a shorter training time will give you quick turnaround. Okay. So yeah, these three networks architecture are recommended, but if you have enough computing power, you are free to use any other architectures out there. Okay. So assuming you are using ResNet 18 as your network backbone. So for there are two subtasks, right? One is you have to train the network ResNet 18 from scratch, right? That means you will do the random initialization of the entire network and train the model using the training set is being provided here, right? So for this chest X-ray data set. Okay, and so you will do the parameter tuning and babysitting your training process and trying to get as higher accuracy as possible on the test set. Okay. For the task 1.2, the other subtask is basically the same. Now for this subtask, we want to leverage the pre-trained model. Okay, we're using the pre-trained ResNet 18 on the large-scale ImageNet, right? And using this pre-trained model and fine-tune it on the target data set, which is the X-ray images. Okay, so we also talk about the fine-tuning. That's the transfer learning part. So you want to basically, I want you guys to compare like which one give you the better performance. Is it trained from scratch or is the transfer learning, right? Using the pre-trained ImageNet model will give you a better performance. Okay, so I also list one very good reference. They give you some of guidance and some of the training tricks or good practice if you want to using CNN for image classification. Okay. So obviously you will write a report, right, to kind of provide the result and provide some analysis. So there's 4 items you have to report in your report. So first is the implementation details, right? Say what network you are using for this assignment. And how are you setting up those implementation details, right? What batch size they are using, right? Image resolution, right? If you are resizing the original X-ray to a particular size, right? If you don't want to deal with the original resolution, then what's the resolution you are using, and the final learning rate, training epochs. So these are very, if you read the papers, right? If you we are reviewing those papers, right? There you will commonly see there's an implementation detail section, right? The authors will list all these implementation details. So if I don't give you the code, then based on these implementation details, I should able to reproduce, the result you reported. Okay, so these are very important. So this is like to reproduce the result. And for the second item, you have to show the training and the validation loss, right? So I provide an example, which will be looking pretty much look like this, right? What's the your training loss curve look like, right? Training, and what is your validation loss curve look like? Okay, so this is help you to kind of analyze or do some diagnosis of your training, right? We talk about, if you have a large learning rate, then your model may diverge, right? You see the loss, drop, then suddenly at some point will go up, right? So there's maybe you have to reduce your learning rate, right? So by visualizing the training loss curve is a good way to kind of monitoring how your model is being trained over the time. Okay. And also it will report the overall classification accuracy on the test set, right? So that means, if the test set has 1,000 images, then what's the overall accuracy for these 1,000 test images? And also report the accuracy for each class, right? So for here, which is very simple, we have binary class, pneumonia and the normal class, right? So you will report the accuracy for individual class, for on this test set. So the reason I wanted you to show this accuracy is see, are you doing well? Is your model perform well on both data set, or maybe, somehow your model is able to perform well on pneumonia, may not be able to, perform well on the normal images, right? Has a lot of false alarm or something like, or vice versa. Okay, this is another way to kind of help you analyze your final outcome. And also the last one is will be useful to present some of the visual cases, right? So which images are considered failure cases, which is misclassified, right? If it's a pneumonia class, but your model classify as a normal class, right? Just to, help you trying to understand, right, what might be wrong. Is this because the this particular pneumonia image is very difficult, visually very similar to normal class, so your model make a wrong prediction, or it's very distinctive from the normal classes, but somehow your model make a misclassification. That's something you can think about and maybe present some of your analysis. Okay. And also I have this optional one that is you can using this CAM or grading CAM, which we'll talk about in this class. So these are two very popular visualization or visual explanation method that is able to help you to understand why the model is predicting such prediction. Okay, so these are the items I'm expect to see in your report. Okay. So when you submit the report, please also submit the code. You can have a zip file to upload, but I think Canvas may have some limit, size limit for your submission. If you have a large file size, so you can host your code on the GitHub, right, and provide the link. Okay, but the bottom line is provide a very clear instruction, right, how to run your code, reproduce the result. So, if you have no instruction and all kinds of different versions of code, it's very difficult for me to understand, right, how to run your code. So you have to be very clear about that. Okay. No, so the report don't have page limit. So basically, you can write as many pages as you want, right? You can present whatever the result you want. You don't have to limit to these 4 items, right? But this is just the minimum requirement. I want to see those details, but you can throw in more analysis if you want, right? If you think that is going to be helpful or useful, feel free to provide those information, right? So yeah. Okay. Okay, again, so this is the deadline. So please work, as soon as possible. So don't wait till like the last week to finish this. Maybe you don't have enough time, right? You may encounter some problems. So, start early. And this is the data set, okay? Well, of course, there's some code because this is a competition. So you're welcome to check some of the code, right? Maybe this is your first time, dealing with this medical image data, right? You want to see how people load the data, is there any common, pre-processing of the data? So that's fine. So you can check some of the common code, but you have to follow my instruction, those 2 subtasks to do the train from scratch and fine tuning. Okay, so this one, the goal for this assignment is just to get you started with deep learning. So you understand what's the whole process, right? Classification is the simplest task. Later for the second assignment, we'll, do the segmentation, okay? All right, so then let's go to the lecture. Okay, so for the past 3 lectures, we kind of go through, systematically from like the simple, feed-forward neural network. Then we go to the convolutional neural network, and discuss different building blocks and how the model is being trained, and some of the techniques, for improving some of the performance, right, like data augmentation, etc. And another very important aspect is the interpretability of the deep neural networks, right? Because deep learning is kind of like a black box, right? You have an input, right? Then you feed these data, a bunch of data, training data to the deep neural network, the black box, and you spit out those predictions, right? If you're doing classification. Hello? Can you guys hear me?
Yeah, we can hear you, Professor.
Okay. Is my disconnected?
But your voice is lacking, Professor.
Okay. So can you see my screen now?
Yeah, we can.
Okay, I guess this is still recording. So where do you guys, where should I start? Like this slide?
Like this slide, from the beginning, Professor, because
Okay.
after that we couldn't hear you.
Yeah. Okay. Okay, great. Thank you. Yeah, so the interpretability of the deep neural network is very important, right? Because, we are training the network, deep learning is like a black box, right? You feed the network with a bunch of training data, and you eventually, make a prediction, right? We want to know like how your model is make such prediction. Is this prediction make sense, right? This is very important for a lot of applications, right? First of all, the safety of the AI models, right? Right now we have, trying to push this autonomous driving, right? The level 5 autonomous driving, right? Like Tesla here. And you want to, understand, right, how your autonomous driving system, making this, decision, right? Why at this point you are changing the lane and you're, stop or, take a, break, right? You want to, be clear, this model, how they are come up with the kind of decision, right? And this is very important for safety. And also for our case, right, medical image analysis, explainability is also very important, right? We are using AI to make some medical diagnosis, right? We are examining these medical images, right, MRIs, to do the tumor detection or analysis, right? We definitely want to know, right, how AI makes such decision, and is this, decision trustworthy, right? So we also need some policy and regulation to enforce that. So, there's a lot of work, towards, this explainable AI or interpretable AI. And, a lot of researchers have been, devoted to work in this field to make everything transparent and, easy to interpret, better interpret the model decision. So if you're interested, there's like a debate, for interpretability of, deep learning. And you can watch this, seminar. So there's a couple of ways we can kind of understand or interpret the deep neural networks. So the very simple one is the visualization of the filters. Okay. So once your model is trained, right? So let's say you have AlexNet or ResNet, DenseNet, etc., or any of the common CNN networks. Once it's trained, we can plot these filters, right? Those kernels are learned, right? So this are some of the earlier layers from AlexNet and ResNet, right? We can plot these filters and visualize what are they look like? What do they look like, right? So maybe these filters behave like edge detector, right? So you have these directional edge. Then here you have different, like focus on different direction of the edge, right? Maybe this filter is sensitive to this pinkish color, and this one is maybe more sensitive to green and the pink, etc. Right? So you can using by visualizing these filters, you get a sense, right? What are being learned from these different layers. Okay. So you can obviously visualize, different layers and see how, they learn different things, among all these different layers. And we can also using the fully connect layer, right? So for the typical CN, we have the convolutional layers, then we append a couple of FC layers. Then the last will be the softmax. You can do the prediction, right? Like 1000 class of prediction for ImageNet. So we can also take, because the immediate FC layer is close to the decision making, right? We can examine, how these feature embedding, is going to impact or affect the decision, right? So we can take maybe the last FC layer, right? Usually it's like 4096 dimensional feature vector. And we can using that feature embedding and trying to find its nearest neighbor, okay? So for example, I have a test image, right? I using the network CN to extract features, I'm isolate or I'm taking that last FC layers, right? 4096 dimensional feature vector. And I can, go through the training set and do the same, and, using the feature embeddings to retrieve the nearest, maybe K nearest neighbors, right? And, see, are these K nearest neighbors make sense, right? So in this feature space, here the example are given, right? We have this test image. If we use the last FC layer to do the nearest neighbor retrieval, and these are the retrieved images in the feature space, right? As you can see that the representation are quite accurate, right? So using the last FC layer feature to retrieve the nearest neighbor, you can see that it's all corresponding to images corresponding to the same class, right? Like this might be a type of flower, and this is the elephant, right? So these are the 6 top neighbors retrieved by using the feature embedding, right? So it kind of makes sense, right? Maybe in this case, you can say your model are making a pretty good representation, right? All these semantics are being captured. The retrieved closest images are pretty much similar or belong to the same class. Okay, so as you can see that as compared to retrieve on the pixel space, right? That is maybe you just take the original image and make that as a feature embedding, right? There's no feature representation, just the original pixel values, and you're using that as feature to retrieve. You can see that the retrieved nearest neighbor is not belong to the same class, right? This is a boat, then you retrieve the image of a horse. And it's easily understandable, right? Because you just look at the pixel intensity, right? Here you have most part is like white pixels, right? And you have this kind of long shape. Maybe this horse also have this kind of characteristics. So the feature is make much more sense to make an accurate prediction. So that's you can using this kind of retrieve the nearest neighbor to see like how to judge like how the model is performed, right? So we can also using some of the technique to visualize the feature embedding. I mean 4096 dimension it's very difficult to visualize, right? In order to visualize, you have to compress into a low dimensional space, right? 2D or 3D, and most 3D you can visualize. So you can using some of the dimensionality reduction algorithms. Like the most popular one is the principal component analysis, PCA. So that is used for data compression. So you can reduce the original feature dimension into 2, and then you can visualize that, right? So you have say you have a training data set, right? You take all these training images, the last FC layer features of these training images, and you do the PCA compressed to 2 dimension, and you can plot these 2D points, right? Each example or each training sample become a point, right? Because we compress them into 2D. And you can plot them and see how these training samples are being distributed, right? So this is MNIST digit classification. So these are actual digits. It's very small, but if you enlarge them, they have different digits writing. So you can see that different digits are kind of clustered together, right? One digit, maybe this is 6. They were grouped into one cluster, and another digit, this is 8. They were grouped into another cluster, right? So this representation is good, right? Because for classification, we want the samples belong to the same class, is very close to each other in the embedding space, right? But samples from different classes, we want them to be as separate as possible, right? So your decision boundary can easily, separate these different classes, right? So we want them within the class very compact, right? But interclass gonna be as separate as possible, okay? So there's another way which is commonly used called the TSNE visualization. So that's also a very common way you can visualize these feature embeddings in the lower dimensional space and see how your features, different samples going to be distributed, right? So those are some of the idea cluster we want to see, right? Very compact within class, but has a large margin between different classes. Okay, so here we'll introduce a very popular visualization method, right? This trying to diagnose this, right? Why the network giving a prediction, right? So for this network, CNN network, you input image and it output a prediction label with 90% confidence, right? This or probability, this is a cafeteria. And why the network give us such prediction? Do you have any visual interpretation? This network make a prediction of 0.9 for cafeteria. So this paper, learning deep features for discriminative localization, introduced this class activation map to help explain the prediction of deep neural networks. So for example, this left image here, right? So the network make a prediction. This is a conference center, right? As you can see that there's a heat map, right? So these red and the greenish, right? Those color indicating the intensity. Okay, the red, more reddish means high, importance or high value on these regions. So for the prediction is conference, as you can see that these heat map is highlighting these region, right? There's a microphone here, right? As you can see, these region are highlighted by these reddish color, or maybe some part of the podium, okay? And also there's another microphone over here. There's a person kind of asking the question, right? The speaker is trying to listen to the question and answer the question. So most like this is a conference center, right? So these regions are kind of play the most important role for making a prediction. This is a conference center, right? These bluish pixels play less important role, right? They have less, importance. On the right, this image, it is predict indoor booth, and why predict such, prediction. And this activation map tells you, okay, though these regions, right, you see these posters regions, highlighting these poster regions. And these are the, most important, pixels the network pay attention to in order to make a prediction. This is indoor booth, okay. So that's the overall idea, but let's see how, we are able to get this, class activation map. And actually the method is, quite straightforward, right? So you have an input and you go through a couple of layers of convolutional layers. Then at the end, you have a global average pooling, right? The gap stands for global average pooling. And so basically it's just for each of the channel, right? So let's say here you have K channels, okay, in these feature map, right? For each channel has the spatial size of H and W, and you take the average, right? So you basically, take average of all these H and W pixels and get a single value, right? So this one, right, this feature map, the blue one, you take a global average pooling, right? You take a global average, you end up with a single scalar, right? And this one, you give you another scalar, okay? So you can, basically for each single channel, you get a single scalar. And then you have a logistic regression, right? You have a weight, then you have this softmax to map your output into the probability, right, between 0 and 1. Okay, and so maybe, here you have a make a prediction dog, which is 0.8 probability, okay. So for the outcome, right, so this is the, if you predict this, the Cth class, right, YC indicating the probability of the Cth class, and it is proportional to this global average pooled value multiplied with the weights, right? So this is just the sigmoid function to map into the range of 0 and 1. So it's proportional to this value here. And because of the linearity, so we can arrange the summation. So you have this WKC FK here together, so with this later summation here. And if you look closely, And this is exactly the weighted sum of all these feature maps, right? So FKHW means each one individual feature channel here or feature map here. And WI is the corresponding weights, right? After you do the global pooling, and this is the weight for each of the global pooled value, right? So here is just a weighted sum of all these feature maps, right? So here, if I make a prediction, okay, let's say I want to see the dog 0.8, right? Then I'm looking at the weights which is connect to this neuron predicting this is dog, right? We have a set of W1 to Wn. Okay, I can take this weighted sum with these feature maps, and ultimately I get this class activation map. Okay, and let's say I want to look at maybe this is let's say this is make up another class. Okay, let's say this is a cat. Okay, and maybe cat has the probability only 0.1. All right, so I want to see if, let's assuming, okay, I want to select this decision. Okay, and what is the network is focused on the image to make a prediction of cat, right? So in this case, I will look another set of values, right? So because this is fully connected, right? So I have another set of weights, right? Maybe W1 prime, W2 prime, and Wn prime, right? So that's the weight. So here, my feature maps will multiply with W1 prime and W2 prime. I can get another class activation map, but this one is corresponding to the decision of making, prediction of cat, right? So maybe, so for this one, I guess if you're gonna make a, prediction of cat, since, in the region, there's no cat exists, right? Maybe you just focus on some of the background or something like that, right? Less important pixels to make this prediction. Okay, so as you can see that you can examine through different classes, right, to check, right, where is this, network pay attention to when they make such prediction. Of course, the most important thing is you want to check the network actually predict, right, the maximum probability, right? So you want to see why your network make this prediction. So here is an example, right? So for this particular input image and the top three prediction, the dome, palace, and the church. Okay, so you can see sum them up is about 0.75 probability, right? So these are the top three predictions, and we can see how each for each prediction, how the network is pay attention to, right? For making prediction, this is dome, and this class activation map is looking at this kind of top region, right? The dome, right? So here maybe look like a dome region, right? So this kind of circular surface. And for the palace, and you can see that the heat map changed, right? The most important part is not the top region anymore. Is kind of in the bottom, right? Maybe the palace or most of the palace in the training data set has this kind of very large building, long building, right? So maybe these are the most important regions the network pay attention to make a prediction that's a palace. Okay, so for the church, okay, it also focus on the top and also maybe focus on the entrance, right? Of the church. So these are some of the highlighted region for the network to make this prediction. Okay. So this is a compile of like a video. So like each frame will make a prediction, right? So you can see these are the predictor labels, and those are red or yellowish are kind of highlight the regions this network is pay attention to in order to make this prediction. Okay, so here like prison, they predict somehow maybe because of this kind of vertical bars, which is very interesting. Okay, here I also present some of the failure cases which the network make a wrong prediction, right? So for this example, the ground truth label is house, but this prediction from the network is sushi bar. And we can visualize the class activation map and see why, right? So as you can see here, this heat activation map or heat map is kind of focused on this region, right? The kitchen sink, right? It kind of looks like a bar, right? Especially you have these kind of tall chairs here, and people behind this kitchen here is like those bartender, behind the bar, right? So it kind of makes sense, right? So this kind of looks like a bar, but for a human, definitely we won't say predict this as a bar, because if we look at other background, right? There's a Christmas tree, there's a sofa, right? So definitely this look more like a house, right? The ambient environment look more like a house. But for the network, they pay attention to this region, then it will make a prediction. This is sushi bar. So this also give you some insight, right? Maybe you have to force your network to looking for more, or diverse features to make a better prediction, right? So you kind of understand, right, why your network make this prediction, or why this is a failure cases. And here's another example, okay? So this is also a failure case, right? So the prediction is martial art gym. But the ground truth, I didn't put it here. I think it's supposed to be an apartment. And it's very interesting, right? So if you look at the highlighted region, right? So it's kind of highlight this barefoot of this person, right? On the ground, on the floor, wooden floor. So if you look at martial art gym, right? Maybe, a lot of, people are just, barefoot, right? That's typical. So you kind of understand, right, why this network make a prediction for this martial art gym. Okay. And this class of activation map also has a very good property that can be used for weakly supervised localization. So for the weakly supervised localization, here mean we use a very weak label, right? So for the fully supervised localization, that is, you have to put a bounding box on the object you're trying to locate, right? So for your training sample, you also have to provide this bounding box so that you can train object detector, right? So you have to give this bounding box as supervision signal. So for the training data, you have to provide this kind of bounding box annotation, which is quite labor intensive, right? You have to, check these images and, correctly locate the bounding box, right? So you can see this is very time consuming. If there's a very dense, right? If you have to locate like multiple persons in this image, and then you have to draw multiple bounding box. So it's quite labor intensive. So for the weakly supervised means we don't provide this accurate label, right, which is the bounding box. Instead, we just provide the image label, okay? We just say this is a goldfish. This image contains goldfish, right? Just give a label goldfish, but we don't provide the label, okay? So we don't provide these accurate supervision, but we just give an image label, right? There's a goldfish. Okay, so we treat this as an image classification problem, right? So because we have the image label, right, we can train an image classifier to predict the image label, right? Say we're using the ResNet to train image classification label, then because the class activation map, right, has the ability kind of locate or highlight the region, make this prediction, right? So if I make a prediction, this is a goldfish, right? I look at this class activation map, it kind of highlights this important region, right? And based on these heat map or class activation map, right, I can set up a threshold, right? Because the heat map also has pixel value, right, intensities. I can set up a threshold and binarize these heat map into a binary mask, right? And then I can, based on the binary mask, kind of to roughly localize the location, right? So I can get a bounding box prediction rather just goldfish. I can even localize where potentially that goldfish, present in this image, right? So that's the, another benefit of this class activation map, right? We can take the image classification problem, but the byproduct is we can leverage this activation map to localize the object, right? So here, another image, right? If we only train image classification model, right, we predict this is a tricycle, but we can leverage this class activation map to localize where this tricycle present in this image, right? So here we can put a bounding box. So this is a very interesting property for this class activation map, right? So we don't have to, manually label all these training samples with bounding box. We can just train a image classifier, but we are able to localize these objects within the image. So here are some of the results, right? So this is the AlexNet. If we train with full precision, that is provide the bounding box, and this is the localization accuracy we get. Of course, right, because this is fully supervised, we provide this ground truth bounding box for the training. It has highest training localization accuracy. But if you look at, they report their class activation map method, weakly supervised fashion, they still can achieve 62.9 accuracy, which is not only like 2 or 3% gap as compared to fully supervised, right? Which is amazing. So there's also some limitations of the class activation map, right? So in order to apply CAM, any CNN-based network has to change the architecture. Basically, you need to use the global average pooling. So that's the one necessary component in their approach. So you have to switch maybe some fully connect layers with these global average pooling. So you're required to do some architecture change. And in the following work, there's this gradient weighted class activation map trying to address this limitation, right? This gradient doesn't require, this architectural change, right? Basically, it can be plugged into any common CNN networks. You don't have to switch, or you don't have to use global average pooling. Okay, and so without using, GAP, we need to figure out a way to define those weights, right? We, kind of collapse the feature map into a single scalar and append with different weights, right, to measure the importance of these feature maps. So for gradient CAM, they just using the gradients of any target class, right? For example, a dog in the classification network, flowing to the final convolutional layer and derive some of the statistics to represent the weights or importance. And here is some of the visualization of the gradient CAM, how you are able to, it is able to highlight, right, the region that is most important for make a prediction, right? So this is the input image, right? If the network predict this is a cat, and gradient CAM is able to provide this kind of visualization, right? So this is the important region it's looking to make a prediction. This is a cat, right? If you look at a class of dog, right, the heat map is changed, right? So the gradient CAM give you the visualization which focus here, right? Focus on the face region of a dog, Okay. So yeah, GradingCam now is kind of like a standard approach for visual explanation because of the benefit of you don't have to change the network architecture. So people are mostly using GradingCam for visual explanation, right? Why the network is making such a prediction. And of course, GradingCam can also use for weakly supervised localization, the same idea, right? So you train image classification, but you have the ability to localize the object within that image. And this is some of the localization accuracy comparison. And also they present a very interesting kind of case study, right? The GradingCam can also identify some of the biases in data set, right? So here they provide an example, GradingCam for biased model, and also GradingCam for unbiased model. Okay, so we can look at these two examples, right? So this one, the ground truth is nurse, right? So the GradingCam highlight this kind of head and hair region. And for the second image, this biased model also predict this is a nurse, but actually the ground truth is doctor. And again, this model kind of highlight the hair, right? This long hair region. But for the unbiased model, right? So both cases are predict correctly, right? So for this unbiased, this one is looking at some of the short sleeve t-shirt region. And for the second image, this one is actually able to focus on this kind of stealth scope region, right? So the reason they call this kind of biased model is maybe this model is biased to gender, right? Because you can see that the model is pay attention to the face, the hairstyle, right? This is a lady doctor, right? So kind of pay attention to kind of the gender region, right? Like long hair, the face, and predict this as a nurse. But for this unbiased model, right, it's just based on some of the characteristics to like the short sleeve, maybe nurse wear that all the time. But maybe for this data set, and also for the doctor, right? This is medical devices is important to make a decision for this doctor. So I think this is interesting, but of course you have maybe have a different interpretation for that, but this is a very interesting, kind of user cases, application cases that is able to kind of give you some idea if there's any biases in the data. Okay, this GradingCam can also be applied in medical image analysis, right? So for this one is the glaucoma diagnosis and localization, right? So for the GradingCam, you can visualize, some of the, regions, why this is a, suspicious area, right? For this kind of glaucoma diagnosis. Okay, so if you are interested more about this kind of visual explanation, so I list these references, so you can get into the details, right? GradingCam. There's also a couple of variants based on GradingCam, mostly improve the GradingCam version to have maybe better visualization or more accurate visualization of the network, right? GradingCam Plus, GradingCam Plus Plus. So you can look at these references to get some idea. And the code is also available. If you want to use GradingCam or GradingCam, this is the code, right? They also provide a demo, so you can upload your image and they will provide this visualization, see if that makes sense. And also there's a PyTorch toolbox called TorchCam. Basically, they integrate different visualization method, right? GradingCam plus, everything's there. So you are also welcome to check that out, since kind of host all different visualization method in one place. Okay, any questions? Okay, so Next, we'll talk about recurrent neural network, right? So we spend a lot of time, discuss convolutional neural network. Recurrent neural network is another type of network that is very important to process, sequence or time series. So for vanilla network, right, so we can have this one-to-one, right? So we have a one input, we generate one output. So for example, we can also using this network to do image classification, right? So we have an input image, we generate output label cat, right? One-to-one mapping. But for the recurrent neural network, because it is capable of process sequences, we can have different type of input and have different types of output, right? Not just one-to-one. We can have a case like one-to-many, right? You have a input, but you can output a sequence, right? So anyone can provide an example, right? So how is an example that can have a one input, but you generate many output?
Not clear, so it might be like image description, like image captioning, like you give one image and it outputs this sentences.
Right, right, exactly. So image captioning, as you exactly mentioned, right? So the input will be image, right? And the output is a sequence of words, right? This is a description of this image, right? A person riding a motorcycle on a dirt road, right? So it's a sequence of words, right? So that's a very classic one-to-many example. And we can also have many-to-one, right? So the example will be sentiment analysis, right? So the input will be a sentence, right? A sequence of words, and the output will be sentiment, right? Negative, positive, or neutral. Okay, we can another example will be video action recognition, right? So input can be multiple frames, right? Maybe 100 frames, but your output will just one class action label, right? Jump, running, etc. And we can also have the case many-to-many, right? So we have many input and also have many output. Okay, so for example, the machine translation, right? So here, example will have the input will be English, a sentence in English, and the output will be a sentence in Chinese, right? To translate. And of course, these, the output input lengths can be different, right? You don't have to be the same lengths, right? Because of different language, they have different, syntax, right? So that result in different lengths. And also you can have the exact same dimension of input as output, right? This many-to-many, you have, 5 input, maybe you generate 5 output. So one example is the video classification on frames, right? So you have say 100 frames, right? I can do classification on a frame basis, right? Every frame I can generate a label, right? So, and eventually I can take the average of all these labels to make a prediction of the entire video. So that's the one example for the many-to-many. Okay, so in the real world, a lot of data application have this kind of sequence data, right? So for example, this stock prediction, right? We are looking at those stock, values, right? At different time, right? Day, second, a minute, right? So in nature, these are time series. And also speech, right? These are also in sequence. And RNN is, very useful because of these kind of, it can do, sequence mapping to like many-to-one, one-to-many, right? Sequence to sequence mapping. So it's able to handle many application cases. So here are some examples in terms of image processing, right? On the left, we can using recurrent neural network to read house numbers, right? To recognize these digits in the house number image, right? On the right, this recurrent neural network is also able to do some image impairing, which means is able to generate some of the missing part of the image, right? By examining some of the existing part, right, in a sequence. So let's look at a concrete example how this recurrent neural network can be applied, right? So let's look at an example that is called slot filling. So let's look at this ticket booking system, okay? So assuming, you are the customer, right? You are chatting to this kind of chatbot from some of the ticket booking system, okay? And you input this sentence, right? I would like to arrive Orlando on November 2nd, right? And this ticket booking system, right? This intelligent system is supposed to extract some information, right? So the two most important information or the slots here is the destination and the time arrival, right? So this is the destination and this is the time arrival, okay? So if we're gonna using a feed-forward network, so how this booking system is able to automatically extract those information and fill into those two slots, right? So first of all, we have the input, right, which is a word, right? We can build some feature embedding from this, from the input word, right? We can using this word to vector approach to map this word into some feature embedding, right? And so for example, we have Orlando here, we can map into some feature embedding. And now each word is represented as a vector, okay? And the output of this feed-forward network will generate some of the probability distribution, right? This input word belong to the slot, right? Maybe this one is the destination, right? How likely this belong to the class or slot destination, and how likely this will belong to the class of time of departure, okay? So how do we do if you input this sentence, right? We can process this sentence word by word, right? So if we take arrive, right, we go through the network and we generate prediction, this may be fall into other class, right? It's not belong to destination or time of arrival, okay? For the Orlando here, we can train a network to make a prediction, this belong to the destination, and on here it also belong to other, and time November and 2nd, this both belong to this time of departure class, right? Well, there's a problem for this kind of system. So if we do this like a singleton, right, one by one, there's some potential problem. So anyone know what kind of potential problem might be? Well, so let's look at this example, right? So if I, also another customer, right? So input this sentence, instead of saying arrive, it says leave Orlando on November 2nd, right? So, we can go through this word by word, right? But from this context, right? Orlando is not destination anymore, right? Because it's leave Orlando, right? It's actually place of departure, right? And because of different word here. But if you train this system, right, the same input will give you the same probability, right? You cannot say, okay, for this one, for somehow this input give you place of departure, right? So you have if you train such a way, right, predict Orlando or other places as the destination, then you have the same input, there's a high chance you still classify this as a destination, okay? So the problem lies in there's no context involved, right? You process this each word one by one, right? There's no context information has been injected or put into this input. So the network is able to understand, right? This is different, right? Because of the sleeve. So in other words, the neural network needs memory, right? It needs to memorize what it has been seen before, right? So before this Orlando words, for this cases, the network has to remember, I see the word leave. Okay, so in this case, Orlando means something different. It's not destination anymore as compared to this case. Okay. And this recurrent neural network is able to build this kind of memory mechanism. Okay, so the output of the hidden layer. Okay, so you have an input layer, you have this hidden layer, right? Then you also have this output layer. Okay, so this hidden layer is able to store the value in the memory. Okay, so let's consider these are the two memory cells, right? To store the output of this hidden layer. And the memory also can be considered as another input, right? When process another input, right? So like first you process arrive, right? Then you have another input Orlando come in. Then when you process Orlando, this word, right? Whatever the value stored in the memory can also be considered as another input, right? So it's not individual input anymore, right? So you have another stream of data or information flow into this hidden layer, okay? So let's run a simple example so you understand this process better, okay? So let's assuming we have this input sequence, right? Very simple two-dimensional vector, right? We have these input sequence. And also for simplicity, let's assuming all the weights are 1, right? So these connection, we have all the weights are equal to 1, okay? And the blue here, right? The memory as input, we also have the weights, right? Let's just assuming everything is 1. And we don't have bias, okay? And all the activation function, right? So the activation function is gonna be linear. Let's assuming y equals to x, right? The output of the activation function is gonna be the same as the input. And so in the beginning, let's initialize the value to the memory, right? Because there's just like the you randomly initialize any neural network, right? We just give some initial random value. Now here we give them 0, okay? So for first input, right, we have a vector 1, 1, right? So 1, 1, these two values here, and we go through this hidden layer, right? So this the output will be 2. Why is that? Because 1 plus 1, and here we have the memory is 0, right? 0 multiplied with 1 is going to be 0, right? We plus 0, basically nothing. So we have 2. Okay, so this output of this hidden layer will be stored in this memory, right? So we have to okay, so we have to run to the output is 4. But once we have this hidden layer output is calculated, we have to update the memory, right? We store this value into this memory. So now it becomes 2. So then let's take the next input from this input sequence, right? Again, it's 1 and 1. Right now, we can easily see that this hidden layer becomes 6, right? Because 1 plus 1 plus 2 plus 2, right? 6. And we go to the output, it is 12 and a 12, right? 6 plus 6. So that's the output. And again, here we can update the memory, right? It's no longer 2 anymore. We update the memory to 6. Then we can run the next input, 2 and a 2, right? So we generate this hidden layer output, and we generate the output, right? If we have more sequence written here, we can keep going, right? We can update the memory and take the new input here and generate the new hidden layer output and the final output. Okay, So eventually we generate this output sequence, right? So if we have more, then we have more sequence output. If we change the sequence order, right? So if we change these input value, right? Maybe 2 and 2 become the first, then the output will be different, right? This is obvious, right? And also because of the memory stored will be different. So we'll change the output. So let's back to this slot filling example, right? So we have arrive Orlando on November 2nd. So we'll take this first word, right? Take the embedding, we go to this hidden layer, we generate the output, right? The probability of arrive in each slot, right? Destination, time arrival, etc. Right? And we'll take that the output of the hidden layer, right? Store that in the memory. When we process the second word, Orlando here, not just the Orlando input here, but we also take the value stored in the memory, right? Taking that into consideration and generate the probability of Orlando in each slot, right? You can, do this again until all the words has been processed. Okay, so as you can see that, now we are able to memorize something we've processed before, right? Arrive, which is one word emitted before the Orlando. Okay. So this is like a graph presentation of this recurrent neural network, right? So you can draw this kind of arrow, back to itself, right? Basically, right, you take the output, store in the memory bank for the next time you use that as an input again, right? So it's like a loop, right? If you unroll that, you can have this kind of the same unit has been repeated multiple times. And for this, the previous example, right? So what's the difference saying leave Orlando and arrive Orlando? Will this recurrent neural network give you different outcome? The answer is yes, right? Because the value stored in the memory is different, right? So for this case, whatever the value generated from the leave is stored in the memory, right? But in this case, the value stored in the memory is different because it comes from the input of arrive. Okay, so this will generate a different probability for Orlando in each slot. Okay, maybe this one, based on the context, it has a high probability of destination. The place of departure. And for this case, we'll have the high probability of destination. Okay. And of course, it can also be deep, right? Just like a CNN as well, right? You can stack, many hidden layers, right, to make it deep. Okay. Another, one type of recurrent neural network which is popularly used is called the long short-term memory, LSTM. It's a bit more complicated. Has multiple gate and so you can multiple input. Right, basically it has input gate, you have an output gate, it has a memory cell. There's also a forget gate. Okay, so like you want to forget some of the memory you store in the memory cell. And each of these gates will controlled by other part of the network, maybe another LSTM module or unit connect to here. Okay. So these are some of the input signal will control these different gates. Okay, so the special neuron consists of 4 inputs and one output, right? So have 1, 2, 3, 4 of the input and 1 output. Okay. So let's see how internally how this LSTM cell works, right? So for this here, we have different gate, right? Input gate, forget gate, output gate. And I also have a memory cell. Maybe you have some initial value, right? C stored in this memory cell. And these are the activation function, okay? So here for the input, right? So we have this ZI control this gate, right? FZI, and it's going to be multiply with this input Z, go through activation GZ, you do the multiplication, okay? And you see here this activation of F, right? These three different gates, right? This is different. And these three gates usually will have the activation function of in the sigma-mod function, right? Because sigma-mod function is able to map any value between 0 and 1. It kind of mimic the open and the close of the gate, right? Because, you know, based on the terminology, these are the gate, right? How large you want to open or close the gate, right? So kind of mimic the open and the close. 1 means you open the gate, 0 means you close the gate. Okay, so we do the multiply. And so for this forget gate, right? So you signal ZF comes in and go to this sigma-mod activation function, you generate FZF, which is a value between 0 and 1, right? So this memory, this value is stored in the memory cell, right? Multiply with FZF, and it's gonna combine with this input, right? GZFZI, right? So this is the kind of refreshed memory, right? C prime. You want to update in this memory cell, right? The reason called a forget gate is that you can see that this is your original memory, right? If FZF equals to 0, right, which means you kind of remove your original memory, right? Just forget about it, right? You just take the new value, right? But if you open the gate equals to 1 or close to 1, right, you still want to memorize some of the old information, right, which may be very important. You want to memorize that, like our previous case, slot filling, right, arrive or leave. You want to memorize those important information so that you can make better prediction. And it goes on, then you can have this output gate, right? Again, you can do the multiplication, and this is your final output. Okay, so that's the mechanism of the LSTM cell. Okay, so there are some limitations of our recurrent neural network, right? So the computation for the position cannot be parallelized, right? Because for the recurrent neural network, you have for each position, you have to wait for the previous memory, right? Your input also relying on the previous cell of the memory, right? So it's not able to do very good on the parallelization. And also long-range interactions are bottlenecked by the fixed size memory, which means you only can memorize some of the short-term memories. You're not able to looking at a very long sequence, right? Like 2 hours long video. You're not able to memorize those kind of long-range information. Okay. There are some example applications here. One is you can using like a hybrid network, right? CNN plus LSTM to do the action recognition, right? For each of the frame, you can using CNN to extract features. Maybe each frame resulting in 1 feature embedding, right? Like 4096 feature embedding. Then you want to take LSTM, right, to model that temporal information, right? Because action recognition, we are not just looking at appearance of each frame. We also have to understand the motion or the dynamics, right? So the temporal information is also very important. So we're using LSTM to model that temporal information, right? For each of the feature embedding come from CNN for each frame, then we're using LSTM to model that temporal information. So you are able to leverage the spatial and the temporal information to make a more informative decision. So for image description or captioning, the same, we can using CNN to extract the feature embedding, then using LSTM to generate output sentence to describe what's going on for this particular image. Video description, the same, right? We can using CNN or maybe here this conditional random field to process each frame, generate a feature embedding. Then we're using LSTM to understand the context of this video, right? What this video is about, maybe doing some instructional video, right? Yeah, here is just a detailed example for action recognition that you can combine CNN and and the LSTM to do the action recognition, right? Each frame go through the CNN to process the feature, right? Because CNN is good at, build high-level representations for the image. Then you're using LSTM to model this temporal information to build the correlations among all these frames. So eventually you are able to, based on the prediction for each of the frame, can be more accurate. Okay. All right, so here I list some of the examples that you can, using LSTM to do some applications like digit classifications, or maybe process some of the time series of data like the stock price prediction. You can using this recurrent neural network to make stock price prediction, because that's somehow highly depend on like some of the history, right? So LSTM is good at model this kind of time series. Okay, so that's all for today. Any questions?
Hi, Professor, I have a question.
Yeah.
So in using the GradCam visualization, do you have any like recommended methods for applying that to scoring? Like maybe you use the GradCam and overlay that with like an image level or a pixel level segmentation, and you say that if it overlaps with these pixels, the the network was queuing on the right features. I'm just wondering how you would maybe apply that instead of just looking at the visualization. How would you apply that to actually scoring performance or something like that?
So using the grading cam to score like different models, is that what you're saying?
Yeah, can you use that activation to get some single value out for your score, or use the visualization to say that the model is performing as expected?
Yeah,
maybe for a large data set or something like
right.
that.
Yeah, I mean, for direct performance, then the most direct is just the accuracy of performance, right? It can help you to determine like which model perform best. That's the direct measure or metric. So the grading cam is mostly used for visual explanation. That's why they mentioned this in the in the paper, right? This is a tool for visual explanation. But if typically you can have multiple examples, just look at a couple of examples, and if you reach a consistent conclusion, right? So you have a model, have multiple examples that the gradient cam visualization is going to be much better than the other visualization of the model. That could be a very good educated, not educated guess, I would say conclusion that one model A is better than maybe model B. So that's the common usage for grading cam. So another usage I want to mention is not just for visualization. It can also help you to improve the model actually. So there are some applications during the training, right? You can using grading cam to highlight the region that make the prediction, right? So that can serve as an attention map, right? You can actually using that map, trying to make your network maybe in the next training iteration to focus more on those regions rather than some background regions, so that your model is able to learn better, right? Just like the grading cam is able to guide your network to attend to the important regions. So that's another, I would say mostly commonly used case, right? How grading cam, not just for the visualization, but is also able to guide the learning of the network so that the model performance can be improved.
Mm-hmm. Okay, thank you.
Yeah, okay. Yeah, so here another one is medical imaging. What kind of application would RNN be more useful than CNN? Yeah, so for recurrent neural network, anything any application that, deal with some of the temporal, or maybe you have to model some relationship between different sequences or different input, right? That's going to be useful, right? So for like, if you process, medical image that has multiple slices, right? One way is people will do 3D convolutional neural network, right? 3D CNN is not just apply a single slice at one time. 3D CNN will process multiple slides at the same time, right? One convolutional kernel will cover maybe 3 or 5, depending on the kernel size, maybe cover 3 or 5 slices, so that you are able to look into spatial and temporal information. But another way is you can use a recurrent neural network, right? Again, just like video processing, right? You can process slice by slice, then you can use a recurrent neural network like LSTM to model that correlation between different slices. And so for some of the like robotics guidance, right, for you are processing videos for some surgeries, definitely you want to consider recurrent neural network to model that temporal information to help you better guide the next step of the surgery. Okay. Okay, all right, guys. Thank you for your time. We're gonna end here, and I'll talk to you next week. All right, everyone, have a nice weekend. All right, bye.
Thank you. Bye.